So let's look at this role of step size a little bit more, because that is one of the things that we need to carefully set. So here I'm showing two different curves, two different green curves, and let's say these two are two different loss curves, right? So we have curve 1 and we have curve 2. So these two curves share a point, and at that point not only the value of the loss function is the same, but also the gradient of the loss is the same. So that is shown by a common tangent line. So if I take a step size which is eta times the derivative, right, the gradient of L, that step size is going to be the same for both loss functions. But obviously what works for one particular loss function or what works for the other loss function is not the same as what works for the first loss function, right? So both of these have different ideal step sizes. So what is different between them? If their function values is the same and the gradient value is also the same, what is different is their second derivative is not the same, or which is called the Hessian in n-dimensional case. So that the Hessian itself is important, or the second derivative is important in finding a good step size. But Hessian is expensive to compute, so we don't directly work with Hessian, rather Hessian inverse in fact. So but suffice it to say that we need two different step sizes for these two different curves. So here's another picture. So let's say we have the same curve. If we have too small of a step size, then we will need many step sizes to find the local minima. If we have too large of a step size, then we might either oscillate from left to the right side of the trough, or we might even increase the loss. And then there is a Goldilocks, or the best step size that is just right, that will find us the local minima in one step, or very quickly with a few iterations. So this step size is decided by the learning rate eta and the gradient multiplied together, but that eta has to be controlled so that we don't have either the situation on the left or the situation on the right. So what is used for that is something called learning rate scheduling. And what happens in that, basically every few iterations we change the learning rate eta, so that either we reduce the learning rate or we increase it, so that we can find good local minimas. The other problem with gradient descent is that we may not even want to have a local minima. We may want to actually escape the local minima and find something which is even lower than the current local minima. So to summarize, we need a good step size, which is not easy to find unless you know the second derivative or you do some sort of second order computation. Okay, we have to do a lot of computations before each update, and we can get stuck in local minima. So for example, let's say if we are in the vicinity of this minima, we will actually get stuck here, whereas we may want to go over this hump and we may want to find the next local minima which is lower than the current local minima. So all these are issues with gradient descent, and some of these can be resolved by using a different version of gradient descent, such as stochastic gradient descent or batch gradient descent. So let's look at what is stochastic gradient descent. So the general algorithm is that stochastically or randomly pick any data point, not all data points. In gradient descent, we were looking at all data points, computing all derivatives and adding them up or taking their average. Here we will randomly pick one training point, and then we will do the update right after that training point. So what we have is, we have iteration loop. Now this iteration loop is going to have many iterations, and that's it. We just have an iteration loop. We don't have an inner loop. Inside this iteration loop, we randomly select one training point, okay, out of the n training points. Then for that randomly selected point, compute Li. Okay, so compute Li and compute this gradient of theta with respect to Li, not the capital L, not the all the entire loss, but loss with respect to just one training point, and then update theta. So theta is going to be theta minus eta of gradient theta Li. That's it. And we keep doing this, hoping that we will hit every training point because we are randomly selecting the training point. Now we will need more updates, right? We are and probably your eta is going to be small, but we are getting updates very quickly. Now what is good for one training point, the update that is good for one training point may not be good for all the other training points taken together. So that's the disadvantage of this method, that it is very greedy and it is working with only one training point at a time. But we are getting updates much quicker. So these are called noisy updates. So sometimes we'll get updates that are overall not good for the loss. Loss, I mean capital L, which is the sum of all the small li's, right? So Li, capital L is, let's say, the sum of all li's or the average of all li's, which is, and Li is the loss for one training point xi. So here we are not worried about what is capital L, we are only worried about small li's. So what is good for one Li may not be good for the capital L overall. So what we are doing is, think about your average loss as some function, right, in terms of in the weight space. What is the x-axis? X-axis is the some weight space, and the y-axis is the loss. Now this function, now let's draw it a little bit more complicated. So let's say this function is like this. Okay, so it has a local minima. Now for it is made up of an average of different losses for each training point, and those different losses have their own local minimas. Okay, so these different losses are with different colors. So the average of all the colors is the red color. Okay, so let's say the average of all the curves. So here, let's say we'll take the average. Okay, we'll divide it by n. So average of all the other losses is the red loss, which is the entire loss, right? And what we are interested in is minimizing the loss for all training points, not for a single training point. Yet we are going to do updates that are based on single training points. And why is that? The reason is that whatever is the local minima for the red curve may not be the local minima for one of the other curves. Okay, so we will not get stuck there. Every time we get stuck there, in the next iteration we'll pick another training point and we'll get unstuck, because that may not be the same local minima for another training point. So we'll keep bouncing around, but hopefully the average behavior of this stochastic bouncing around is that we will settle into the local minima of the average curve. Okay, so we will escape the local or global minima of the average curve. We will escape the local minimas of all the other individual curves that make the average curve. So that is basically the idea behind stochastic gradient descent, that it will help you get updates quicker. You don't have to go through all 1 million training points to get one update. And second, because of this stochasticity, your weights will bounce around the global minima, but as you reduce the learning rate, finally you will start to settle towards the global minima. That is basically the idea of stochastic gradient descent, and that has been proven through by assuming certain things about the smoothness of the loss function, and based on that, mathematically it has been proven that stochastic gradient descent has some nice properties that help you get to the global minima or within a tight band of the global minima. Now the disadvantage of this stochastic gradient descent is that when we compute the function, the loss and the gradient for one training point, we forsake a lot of computing power that is available in modern machines. So especially when you're using GPUs and you have few thousand cores in your GPU, the cores are not sufficiently engaged to compute this loss and the gradient of loss for just one training point. So what do? instead of we go for something that is in between the vanilla gradient descent and the stochastic gradient descent, and basically that is the de facto method these days for training neural networks, which is the batch gradient descent. So this has basically one loop that is outside, and that loop is for batch formation loop or batch formation block. So in batch formation, let's say if you have 1 million training points, we randomly shuffle them and then we divide them into batches. Okay. And we will compute the gradient for one batch at a time. So we are not computing for one sample at a time, we are not computing for all the samples together, we are doing something in between. We are computing the gradient for one batch at a time. So these are randomly shuffled. So these are already shuffled with all the training points are shuffled anyway, and after that we create the batches. And so batch formation is shuffle training points, okay, and then create batches. Divide the training set into batches. Then we have an outer loop. That outer loop is for epoch loop. One epoch is when you have gone through all the batches, and inside that you have a batch loop when you are going through all the batches. Okay. In the batch loop, we are computing L batch Li, where I belongs to batch, this batch. Okay. So let's say J, batch J. All right, and then we are similarly computing del theta of batch. And then we are basically updating the parameters based on the batch. Okay, so we are getting updates after each batch. We don't have to wait until the end of the epoch to get an update. And the randomization comes from the batch creation itself, because of which for what may be minimum for one batch will not be the minimum for the next batch, but overall for all the batches taken together, we should be able to escape local minimas, and we should be able to find the global minima using based on this stochastic behavior. So this batch gradient descent, so what is the advantage of the batch gradient descent? The size of the batch is such that you can utilize your entire GPU memory with one batch. So you keep increasing the batch size until you get a memory error, and that is a good batch size usually to start with, and based on that you can train your neural network. Sometimes varying the batch size also helps you escape local minimas. So the batch size itself becomes a hyperparameter in practical cases, that you play with the batch size. Your maximum batch size will be determined. What is a batch size? The number of samples you can fit in a single batch. So this size is the batch size, this is the number of batches. So batch size times number of batches is the total number of training samples. So your batch size is a hyperparameter, but it is the upper cap on the batch size is what can fit in your GPU memory, that doesn't give you out of memory error. So now let's look at how we can speed up gradient descent using the concept of double derivatives, which is the equivalent of that in n dimensions is going to be the Hessian. So quickly revising that if you have a perfect quadratic function ax squared plus bx plus c, then we can find its minima in one shot, which is basically going to be minus b by a and minus b by 2a rather. And how that comes is that basically you have this f of x, which is ax squared plus bx plus c. Your f dash is 2ax plus b and f double dash is 2a. So if you can see this convex function here, so this blue curve is your convex function, and then we have its first derivative, which is the red line, and it is always positive, right, because it's a convex function, and always positive sloping, sorry. And we have the green line, which is a second derivative, which is positive in this case, which means that it is the second derivative is a constant positive, and for a concave function it is opposite, as seen on the right hand side. So wherever the red line cuts the horizontal line, that is the point where we can find the minima of this function, and c does not matter in that case. So here, if we want to do this using gradient descent, then we would need to find a perfect step size, and if we knew the knowledge of 1 over f double dash of x, which is the second derivative, inverse of the second derivative, we could find the minima in one step, right? So here you can see two different curves, the red curve and the blue curve. They have two different equations, right? And basically they have two different a's. They share a point where the tangent is also the same. Obviously the second derivative is different for them, which means that 2a is different for them, which means that the ideal step size is going to be different for them, for the two of them. The perfect step size for a paraboloid, so let's say if we have ax squared plus bx plus c and a is less than 0, we know that the minima lies at minus b by 2a. So your perfect step size is going to be 2ax minus 2ax plus b divided by 2a, which is minus of f dash x divided by f double dash of x. So if you think of this as the gradient, then this is your step size. So your perfect step size is 1 by f double dash of x. So this is the second order method for speeding up gradient descent. In n dimensions, there's no double derivative. What we'll have is Hessian. So we will have the Hessian inverse, okay, times the gradient of f. Now this Hessian inverse, if you have 1 million parameters in the neural network, your Hessian is going to be 1 million times squared, right? So it's a square matrix, and inverting that would be will take order order n to the power 3 or n to the power 2.6 operations for inverting this matrix. So that's a very expensive operation, and for non-convex functions which we are after, the functions where the eigenvalues of the Hessian are not always positive, right? In those cases, when we have saddle points and such, actually using a second order method actually attracts you towards local saddle points, and that's not the behavior that we want. So we don't use this. What we use is a different method. We use approximations to the Hessian or approximations to the absolute value of these eigenvalues of Hessian that leads to speed up. So let's come to that discussion in a bit. I will talk about one particular method, which is momentum, but let's just complete our discussion of a Hessian vector. So this is, let's say, a paraboloid. So here if you look at any particular point, let me change the color so that we can see it better. So let's say we take any particular point. Here we have the gradient is a two-dimensional vector because it has to give you the x direction and the y direction for the largest increase in the function, and their correlation between those two directions, etc., is coded by the Hessian matrix. So this is the Hessian matrix. So an example of that would be, let's say, if you have a two-dimensional function with x1 and x2, the gradient can be computed as such, and the Hessian can be computed as such. And for a particular value of x1 and x2, we can find what is the second derivative. Here, I think the Hessian matrix is constant. That is because it's a perfect paraboloid. So that's why the Hessian matrix is constant. Just like for a parabola, the second derivative is a constant. So now we don't have these perfect paraboloids in the loss function of a neural network. What we have is very complicated shapes. So let me show you an example. This is what is going to be more closer to reality when you look at W1 and W2 as 2 dimensions and the loss with respect to W1 and W2. We are going to see complicated shapes like this. So one direction is W1, the other direction is, let's say, W2, and what we see is that we are after some global minima, but we have these local peaks like local maximas, we have local saddle points. So what is a saddle point? Basically, in one direction it is going down, it is like a maxima, in another direction it is like a minima, just like a saddle on a horse. If you, where your legs go, that's where the saddle is going down, but towards your front and towards your back the saddle is going up. So in the direction of the back to front of the horse, you are at a local minima, but in the direction of side to side of the horse, you are at a local maxima on the saddle. So the way, and now this direction can be, the whole saddle can be rotated with respect to some arbitrary axis W1 and W2. So because you can rotate it, these directions can be combinations of W1 and W2 and not just simply in the W1 direction or the W2 direction. So because of that, we look at eigenvectors of the Hessian matrix and not like individual weights themselves. So if you look at the eigenvectors of the Hessian matrix, the eigenvalues define whether we have a maxima or a minima. Positive eigenvalues means we have a minima in that direction, and negative eigenvalue means we have a minima in that direction. So we can also have some positives and some negatives. That's exactly what a saddle point is. When we have all eigenvalues as positive, then we will get a local minima, and when we have both of them as negative, we'll get a local maxima. So here, going back to this slide, this is a local minima. So the trouble usually is not to find the local minima in neural networks. The trouble usually is not that you get stuck at a local minima. The trouble usually is that there are all these other structures in the surface of the loss function in which we get stuck. One of them is this saddle point, right? So in one direction we have a maxima, in another direction we have a minima, right? So we can get stuck here, especially when we are using a Hessian based computation. Other could be like we have long furrows. So think of like half a pipe, like a drain pipe, right? So in one direction we have almost zero gradient, right? In the other direction, in the transverse direction, we have a minima. So here also we can get stuck here. We don't know whether to go here or whether to go here in that drain, right? So let's say this drain is flat, not like sloping. And so these are the more interesting points. So that's why the point that I'm trying to make is that we are not obsessed with finding the global minima of a neural network. If we can escape saddle points, if we can escape long furrows, that is good enough, and we find a local minima so long as we have done some stochastic behavior around it to test that it is deep enough for local minima. That is usually good enough. And there are certain theoretical results that suggest that usually local minimas are almost as low as within a tight band of the global minima itself. Another important reason to not obsess about global minima is that global minima of what, right? Global minima is a global minima of training data, not of testing data. So when it is global minima of training data, there's no guarantee that it still works well for the testing data. So that's another reason we don't obsess about finding global minima of a neural network with respect to the training data. So now that we know that it is not important to find the global minima, but just escape some local minimas and saddle points and so forth, how can we do slightly better than gradient descent to do that? And this is the final concept of this module, and which is that we will use something called momentum in lieu of the second derivative. We'll not use a second derivative, but we'll use an easier to compute concept. So otherwise we would have to compute second derivative is not just second derivative, it's a Hessian matrix, and we would have to invert it. So we'd want to avoid that, but we'll use momentum. So in momentum, the update is going to be like this, that we will have theta, which is going to be updated by the previous value of theta, okay, minus eta times the gradient of theta, gradient of loss with respect to theta, right? Okay, and we are going to add one of the previous updates. So let's call this now L, So let's call this iteration, n. Okay, so iteration n, and this is for iteration n minus 1. Okay, this is the previous weight. Okay, in addition to that, we will add some factor alpha of the previous weight update, which was theta of n minus 1 minus theta of n minus 2. Okay, so notice that the dimension of this, the dimension of this, the dimension of this, and the dimension of these all are consistent, which is the number of free parameters in the neural network. All of them are the same. Now, what does this alpha do? This alpha is a constant factor which is between 0 and 1. It belongs to this range 0 and 1. Okay. It cannot be above 1. When you have it above 1, then you will have too much speed up in the direction of previous updates and you will get unstable behavior. If it is below 0, then it will have opposite of the effect of momentum. What is momentum? Something that stays in motion, something that is in motion tends to stay in motion. Something that is decelerating is or something that has stopped tends to stay stopped, and so forth, right? So it's a similar concept. So basically, let's say if you are in a flat region of a loss curve. Okay, so this is loss and this is weight. Okay, if we are in a flat region of a loss curve and we make a small update last time, whereas we should have done a large update to escape, let's say, and find another a better minima. So we want a larger update, but we made a small update because of some reason. So if the previous update and the current update are in the same direction, right? If they are in the same direction, then we are going to keep adding them via factor of alpha, and the next subsequent steps are going to be bigger and bigger, and we will we will speed up the convergence in that case. On the other hand, if we are in some sort of if we are going too fast, then we have positive gradients, negative gradients, and so forth. Then these two terms will have opposing signs. So when they have opposing signs, then it has a braking effect on the momentum, or let's say if it is like here, it will have a braking effect and it will try to settle down in this trough, as opposed to like shooting out of the trough. So momentum can have either a braking effect when you are bouncing around a lost trough, or it can have a speed up effect when you are in long furrows of the lost trough. So that's how we can speed up the convergence of the neural network. This entire momentum equation can be plugged into batch gradient descent, stochastic gradient descent, or the vanilla gradient descent. A good value of alpha is around like 0.8 or 0.9. Those values work very well, but that again becomes another hyperparameter or something that you play around with in practical terms when you are training a neural network. Other ways, there are other better methods of speeding up convergence, such as Nesterov momentum or RMS prop or ADAM, which are out of scope for this course, but you can read up on them and you can use them as a library call in popular neural network training libraries for different software. With this, we reach the end of this module. So to conclude, basically neural networks, they are a generalization over linear regression or logistic regression by adding more outputs and more layers in the function, and they're trained in the same way as logistic regression or linear regression would be trained, using gradient descent, but where the gradient descent is computed more efficiently for large number of layers by storing local gradients and using the chain rule. And the same concepts can be applied here of regularization. So just like we had L2 penalty on weights for logistic regression and linear regression, we also have L2 penalty on neural networks. So basically here we also have minus some lambda by 2 times theta, right? So we can add that as an L2 penalty, gradient of L2 penalty also, sorry, plus also on the I'm sorry, it's going to be minus because it's the negative of the gradient. So we can add that also here in gradient descent of neural networks, just like we did for logistic regression and linear regression. And that term in neural network parlance is not called L2 penalty for some reason. It's called weight decay for historical reasons. Weight decay, but it is basically nothing but L2 regularization. Right. L1 regularization is not very well used in neural networks because L1 regularization will turn some of the weights off, make them zero, and we don't know how to interpret that in the neural network, that some of the arrows are missing in the neural network. So we don't usually use L1 penalty, but L2 is quite heavily used, and then this lambda becomes another hyperparameter that you tune when you are training neural networks. With this, you can model a whole bunch of nonlinear classification as well as regression functions. Thank you.